Happy Tuesday, you guys. Just gonna jump on here and do number 4 quickly. I'm hoping a couple people asked about number 4, and then 1, 2, and 7 were on my radar as well. But I'm hoping an explanation number 4 might help with 1, 2, and 7. So number 4 says a basin has the shape of an inverted cone with an altitude, which is going to be really the height of 6, and a radius at the top of 9. Okay, so I actually tend to like to draw these like this so that I can see that right triangle. So 9, 6. Water is running in at the constant rate of 3 cubic centimeters. So that's cubic centimeters is volume. So the rate of change of the volume is 3 cubic centimeters per second. At the instant when the water is 4 centimeters deep, so the depth of 6 is changing and the radius of the top of the water is also changing. So for instance, when the water's only up this level, whatever number that might be, the radius would only be that big as opposed to the 9. So the point is that the radius to the depth is always going to have a ratio of 9 to 6 or 3 to 2. So 2r equals 3d if I cross multiply there. So at the instant when the water is 4 centimeters deep, so at the instant when d equals 4, find the rate at which the level of water is rising. So that is your rate of change of the depth. So d dt is what we're looking for. So since we have the rate of change of the volume, we're going to focus in on the volume of a cone formula, which is 1/3 pi r squared h. Now we can figure out the volume at that depth instant. 1/3 pi r squared, we can find out the r at that instant. We would need a dr dt, and we would need, or we don't actually need it because it's what we're looking for, the dh dt. I'm going to go back and call all these h's in hindsight because that's what we call the height in the volume formula. Okay, so this is what we're after. Since we're after dh dt, rather than introducing a dr dt, sometimes I think it makes sense to, since we know we need the dh dt, I think it makes sense to replace the r prior to differentiating. So in this case, I would replace my r with 3h over 2. So if I do that prior to differentiating, that's going to make this a little bit less complicated. So 3h over 2 squared h. I'm going to crunch that to 9h over 4 times h. Squared, the h is squared. 3 squared is the 9, h squared is h squared, 2 squared is 4. And so when I clean this all up, it's 9 pi h cubed. 9 pi h cubed. This is over 1. This is over 1. So 9 pi h cubed all over 12. And that was silly because 9/12 is 3/4. So there's a different version of my volume formula, knowing that r always has to be 3h over 2. So now I'm going to differentiate, and I'm going to get that dv dt equals, now I can use just a straight power rule. See, rather than having to do a product when you have two variables involved, I'm just going to do a straight power rule. Bringing the 3 out in front makes that 9 over 4 pi h squared dh dt. And this dh dt is what I'm after. So I know dv dt, they've told me that's 3. and they want to know at the moment that the depth or the height is 4. So h is replaced by 4, and that leaves me with dh dt. Now this 4 is going to cancel with one of those, so it leaves me with 3 equals 36 pi dh dt. Divide both sides by 36 pi to get rid of that. 3 over 36 is 1 over 12 pi equaling dh dt. So when we jump to part B, okay, we talk about the rate of increase of the exposed surface area of the water. So I'm thinking that is the rate of increase of this area right here. So that's just the area formula there is just pi r squared. So if we want the rate of increase of that surface area, we want to differentiate this. So dA dt equals, now again, this is in terms of r. Since I know all these, I don't know dr dt yet, and I didn't actually take the time to find out r at this instant yet. So actually, if I wanted to, prior to differentiating, I could again make that r in terms of h, because I know all the h information. So rather than pi r squared, I'm going to change it to pi 3h over 2 squared. I'm going to clean that up to 9 pi h squared over 4, or 9/4 pi h squared. So when I differentiate, bring my 2 out in front, I'm going to get 18 over 4 pi h dh dt. And I already know what dh dt is, so I'm going to have 18 over 4 is 9 over 2 pi. I know that h at this moment is 4, and I know that dh is 1 over 12 pi. So this pi and this pi cancel. This 2 and this 4 reduce. The 9 and the 12 reduce to 3 and 4. This 2 and 4 reduce. So I end up with just 3 on the top and 2 on the bottom. 3 halves. And I guess it's the rate of surface area, and we are in centimeters, so area is centimeters squared, and it's a rate, so it's per some unit of time, so per second. So hope that helps. The videos you guys are watching I made 2 years ago, so I feel like maybe the transition was right around then, but I started to substitute things out early on, kind of the way I explained here. Since I knew my focus was on finding dH dt, I found a way to get rid of that r and put it in terms of h and clean up the original equation first, so that when I differentiated, number 1, I didn't have to do a product rule. Number 2, I didn't have to worry about dr dt's floating around alongside dH dt's. Maybe I made that clear in the video already. Maybe if I tried to, this for whatever reason makes it settle in a little more, or maybe I was teaching it a totally different way 2 years ago. I can't even really remember, but I think I found that that's the most clear way. And same thing down here. Maybe people's trouble here was the surface area, not realizing just area of a circle, pi r squared. But again, rather than differentiate the pi r squared, which would require me to have to go find my r, which I could do. I could definitely go back with a depth of 4 and figure out what the radius is at that point. But I'd also have to figure out the dr dt. And so rather than mess around with that, since I had already found the h information, some substitutions there, on the front end of it, make my job a little bit easier and don't have me figuring out everything under the sun. So if that doesn't clear up 1, 2, and 7 for people, feel free to just shoot those back at me, and I will jump on those as well.